All right, this lesson is about Chapter 2. In Chapter 2, we're going to start wading into atomic theory, and we'll also get into naming ionic and covalent compounds. And this is the chapter before we get into looking at quantum mechanical theory of the atom. So another foundational chapter based on what we know from late 1700s up through the 1920s. That's going to be the focus of this chapter. So the thing to remember about this chapter is that you look at the next slide here and make sure you change every one of these things into a question. What is atomic theory? What is the structure of the atom? What is the atomic number, mass number, and isotopes? And if you can answer those questions after each one of the sections in the chapter, then you understand that material. And you've got the Learn Smart module for Chapter 2 to help you determine if you're comprehending what you're reading, and you'll have the assignments for Chapter 2 to see if you understand the mechanics of this chapter. So the first thing I want to talk about is atomic theory. And what I want you to remember about a theory that we talked about in Chapter 1 is that theories are human constructs. Theories are based on observation, hypothesis, experimentation, series of experimentation, and then conclusions. And from those conclusions, we see a pattern, and we label that as a theory. And the reason why we like theories is theories hopefully allow us to predict future events. And that's the whole advantage of a theory, is that it allows us to interpret or predict future events or things that are happening. So atomic theory starts, that's the foundation for chemistry, and that starts with Dalton. So Dalton published a book, the Principia, and he is the first one to write down all these different postulates of what atomic theory is, so, or the foundation of atomic theory. So first of all, he said, and they're not all true. Today we know that they're not all true, but they come pretty close. So the first thing he says, just like we said in Chapter 1, that elements are a group of extremely small particles that we call atoms, and all atoms within a particular element are identical. They have the same size, mass, and chemical properties. And that one atom from one element is different from an atom from a different element, from a different atom that is a different element. All right. So each group of atoms that have identical properties, there are different groups of those atoms, and we call those elements. Now, we're going to find out this isn't always true, that you can have different masses in the same element. But a group of atoms that have identical properties we define as an element. 2 is compounds are composed of 2 or more different elements. That's what I want to say. He says atoms of more than one element. We want to say 2 or more different elements form a compound, and they have a fixed whole number ratio of one element to another in the compound. So we've talked about this in class. We said that if we look at water, that water is H2O, and so if it's H2O, it's 2 atoms of hydrogen bonded to 1 atom of oxygen. Fixed whole number ratio, is a pure substance, is a substance. And remember we said compounds can be broken down into elements by chemical means. All right, so that's kind of tying in with Chapter 1. You got to master Chapter 1 before you can get into Chapter 2. All right, and then the third one, this is the really important one to me. In a chemical reaction, all we do is rearrange the atoms. It does not create or destroy them. So chemical reactions do not create or destroy atoms. And that comes about by, if we look at Antoine Lavoisier, he had a container and he had a vial of liquid and he knew what the mass of it was. And he had a vial of liquid, he knew what the mass was. And he puts this in a bell jar and he sucks all the air out of it and he weighs it and it has a mass. He then mixes this up and this liquid mixes with this, and so after his experiment he has a container, the vials are spilled over and the liquid is gone. And he weighs the mass and it weighs exactly the same. So before Antoine Lavoisier, who's considered the father of modern chemistry, we would think that this vanished, that it disappeared, that it no longer exists, especially if the liquids become a odorless and colorless gas. So by carefully controlling the variables in the experiment, namely that it's sealed and nothing can escape, and he notices the mass doesn't change, he says that matter is not created or destroyed in chemical reaction. Now, you go, why do I need to know that? Well, when people say I can churn lead into gold, and these are the elemental symbols for lead and gold, that can't be done chemically. There's no way you can chemically change lead into gold. In order to change lead into gold, we're going to find out you're going to have to change the number of protons in the nucleus. But we're talking in the 1800s here, early 1800s, Lavoisier's experiments, late 1700s. And so just looking at this experiment, he knows that things don't vanish, things aren't destroyed, we don't create something out of nothing, that it all has to be accounted for. And that's a powerful statement. That is the foundation that changes chemistry from alchemy and magical to a science. So Proust Law. Proust was working with ratios of gases, and what he noticed was this, is that carbon dioxide was a gas, and that he could weigh 123 grams of carbon dioxide, or 50.5 grams, or 88.6 grams of carbon dioxide, and he could break that down into the amount of grams of oxygen and carbon in the compound. So if you have 123 grams of carbon dioxide, 89.4 grams were carbon, 33.6 grams were, 89.4 grams were oxygen, and 33.6 grams were carbon. And if I had 50.5 grams of carbon dioxide, 36.7 grams were oxygen, 13.8 grams were carbon. So when he looks at the mass ratio of oxygen to carbon, so grams of oxygen to grams of carbon, doesn't matter how much carbon dioxide he has, the mass to mass ratio of oxygen and carbon is 2.66 to 1. So there's 2.66 by mass grams of oxygen for every gram of carbon. So it's called the law of definite proportions. Notice there's no interpretation here. It's directly measured. I take this, I break it down into its elements. So we take a compound, break it down into its elements, oxygen and carbon, and the ratio always comes up to be 2.66 to 1. Doesn't matter how much we have. So that's the law of definite proportions. So that gets us on the path of what is an atom, because once we know that if we call it carbon dioxide, it's always 2.66 to 1 by mass. Then, if we do carbon monoxide, where we know it's we got one carbon and one oxygen, the ratio always comes out to be 1.33 to 1 by mass. 1.33 grams of oxygen for every 1 gram of carbon. And if we compare these two, if we compare 2.66 to 1 gram of carbon and 1.33 grams of oxygen to 1 gram of carbon, if we compare those two, watch what happens. We get a ratio of oxygen to carbon to be a whole number, 2 to 1. We take 2.66. Both of these have a common denominator of 1 gram of carbon, so we can divide 2.66 by 1.33 and we get a ratio of 2 to 1. And so Proust was able to figure out that carbon dioxide is 1 atom of carbon and 2 atoms of oxygen. And carbon monoxide is 1 atom of carbon and 1 atom of oxygen. It's 1 to 1. So this is called the law of multiple proportions. So what this is saying, this law, it's not a theory, it's a law, it's directly observable, is that atoms combine in whole number ratios. You can't have hydrogen and a half of an oxygen. What you have to do is multiply this by 2 so that you get 2 hydrogen atoms and 1 oxygen atom. And then the next compound would be, you got HO, and if we multiply that by 2, we get H2O2, and that's hydrogen peroxide. So this is really important because now we say an atom is a pool ball, that you either have an atom or you don't have an atom, and atoms always combine in whole number ratios. You can't have half of an atom. You either have one or you don't. So that's why when you look at chemistry, a lot of times we look at it as atoms like being pool balls. There's a carbon, there's an oxygen, there's an oxygen. They combine in a whole to whole number ratio. Law of multiple proportions. All right, so we have a problem here. We have both water and hydrogen peroxide are composed of hydrogen and oxygen. So we're talking about 2 elements here and 2 different compounds. Water, when it decomposes, produces a ratio of 0.125 grams of hydrogen for every gram of oxygen. And when we decompose hydrogen peroxide, it produces 0.063 grams of hydrogen for every gram of oxygen. So they want you to determine the whole number ratio of grams of hydrogen to 1 gram of oxygen in water and the grams of hydrogen to a gram of hydrogen peroxide. And this will illustrate the law of multiple proportions. So the common denominator is, this is for every gram of oxygen, this is for every gram of oxygen. So if I divide 0.125 by 0.063 grams, what am I going to get? Well, that's about a 2 to 1 ratio, right? Doesn't come out to be perfect because of experimental error. But 0.125 divided by 0.063 is 2 to 1. So this is saying there are 2 hydrogen for every 1 oxygen. And so we know then that water is H2O. And I think this is remarkable. You're talking to early 1800s, and they know that water is H2O at that point. With this just careful measurement of mass. Careful measurement of mass and the properties of hydrogen and oxygen. Great observation. Okay, so let's look at another one. Sulfur and oxygen can combine to form several compounds, including sulfur dioxide and sulfur trioxide. All right, in sulfur dioxide, we have 0.9978 grams of oxygen for the common denominator of every gram of sulfur. In sulfur trioxide, we have 1.497 grams of oxygen for every gram of sulfur. What I want you to determine is the whole number ratio of grams of oxygen to 1 gram of sulfur in sulfur dioxide and to grams of oxygen to grams of sulfur in sulfur trioxide. So let's have you try that and let's see how you do. So stop the video and see if you can determine the whole number ratio of oxygen to sulfur in both sulfur dioxide and sulfur trioxide. Okay, so in sulfur trioxide, I think it's so it's funny. This person's using the the English version of sulfur. This is the American version of sulfur. All right. So sulfur trioxide is 1.497. Sulfur dioxide, it's 0.9978 grams of oxygen based on 1 gram. There's a lot of typos here. Grams of sulfur. And so we get 1.50 to 1. And so you're going, oh, well, that doesn't make sense because you said it always has to be a whole number. You can't have half of a gram or half of an atom. So when you get something that looks like this, you're going to have to multiply this entire thing by 2. So by multiplying by 2, you get a 3 to 2 ratio. All right? So this is 3 to 2 ratio. So this one, sulfur trioxide, SO3. This one down here, SO2. So again, you can't have half of an atom when you get a fraction, and the ones you got to be aware of are 0.25 is 1/4. 0.33 equals 1/3. 0.5 is a half. That one's an easy one. 0.67 is 2/3. And 0.75 is 3/4. So just keep that in mind that if you get these fractional amounts, you know the atom occurs in whole numbers. You're going to have to do some conversion there. You're going to have to do some multiplication. How do you fix this? Whatever the denominator is, that's the multiplier. So this one, it was 1.5. So 0.5 is equal to 1/2. I don't know what I put it. Yeah, 1/2. So I multiplied this by 2 to get rid of the 0.5. All right. So just keep those come up over and over again. So you may want to write those down. All right, so we're in the 1800s, and people, after reading Dalton, they say, okay, this is what the atom looks like. It's a pool ball. Looks like that. Solid sphere. Each one of these spheres has chemical and physical properties, and when we have a group of identical atoms, we call that an element, and they're defined on the periodic table. They have different, each group of atoms that have the identical size, mass, chemical properties, and so forth. So that's what the atoms look like in the 1800s, early 1800s. Okay, so in the 1800s, we're really experimenting with electricity. And so let's talk about this cathode ray tube. And I don't know why they put this slide first. Let me go to the next slide and show you what we're really dealing with here. So in the 1800s, we have a tube like this, and I can't think of what the name of the tube is now. It's an Italian name. So this is a tube. You suck all the oxygen out of it, and you have an electrode here, and you have an electrode here, and they're connected to a battery here, and they're connected to the other battery end there. And then what you have in here is you've got a piece of paper that is coated with the element phosphorus. And phosphorus, when it's excited, it glows. And so when we connect the battery terminals together, we see these rays emanate across the phosphorus like that. And so Thomson, J.J. Thomson, he maybe starts with the magnet here, and he notices that when he puts the, south pole of the magnet, and it doesn't matter here, one's a positive end and one's a negative end of the poles. If he puts the positive end of the pole, this beam bends towards the magnet. And when he puts the negative end of the pole, it deflects away from the magnet. And so he realizes that this ray that's coming out of this plate here, and he knows the direction, so he knows the negative plate and the positive plate, and because it's coming from the negative plate, he calls it a cathode ray. It comes from the negative plate, so he calls it a cathode ray. All right. So he does it. So let's go back to the other. Let's go back to the other slide to show you what's going on here. All right, so pretty much what we just saw was this part. We have an electrode here, an electrode here in a vacuum, and there's a ray that comes off of this cathode, this negatively charged. This goes to the negative end of the battery. This is to the positive end. Now, in this apparatus, they have a hole in the anode, so the beam goes through the hole, and the magnets keep it collimated, keep this beam on path here. All right. Now we have a positive plate or negative plate here. There it is, and a positive plate here, and there it is. All right. That's positive. That's negative when we flip the current onto it. But before we flip the current onto it, the ray goes straight through, and it hits this glass. This is kind of the precursor to the TV. So what a TV does is it has a cathode ray, the old TVs, and they would scan like this across these phosphors, and it either kick the phosphor on or kick it off, and you had black and white TV. And it happens so fast that you see this image on the front end here, and you say that and if it keeps moving, it can make it look like some animal or something's moving across the screen. Black and white TV. Now, the more primitive form that you see in a lab is, this is generally coated with green phosphorus, and you see one bright white dot in the center of the phosphorus screen. That's this beam coming straight out and hitting the phosphorus and glowing. Well, when Rutherford kicks on this positive and negative plate, he notices when this plate's negative and this one's positive, the beam bends downward like this. So what does that tell him? Well, we know opposites attract, so he knows that this beam is negatively charged. He knows the beam is negatively charged because it's attracted to the positive plate and it's repelled by the negative plate. So J.J. Thomson is given credit for the discovery of the first subatomic particle called the electron. All right, so that's his experiment. He determines that the cathode ray consists of these particles that are negatively charged, and he calls them electrons. Now, he knows that they're negatively charged. He doesn't know what the actual charge value is, and he doesn't know what the mass of the electron is. So all he discovers is that the electron is negatively charged, and he gives it the name electron. Okay? So that's what he determines. That there's a negatively charged particle in an atom called an electron. But he doesn't know what the actual charge is, and he doesn't know what the actual mass of the electron is. He knows it's negative, but he doesn't know the magnitude of it. All right, so along comes Milliken. So Milliken takes some oil, uses an atomizer like a perfume atomizer. He has a metal plate here that is positively charged and a negative plate at the bottom here. He puts a hole in the positive plate, and he has an X-ray source here that can knock or add electrons to these oil droplets that go through the chamber here. And then he has a microscope to see what's going on right here in the field with that dot of oil. So let's talk about what he's doing here. He squeezes the bulb, which sprays out these little droplets of oil. Now, oil has mass. We would expect every once in a while one falls right through this little hole and it falls right to the bottom like so due to gravity. All right, so an oil droplet falls through the hole and it's falling, and then all of a sudden we irradiate it with this X-ray source, and then he can adjust the current between, or the potential energy between this plate and this plate. He can adjust the voltage. So he can actually make the oil droplet levitate to stay right here in the field of the microscope. So that means this now has a charge on it and that it's attracted to the positive plate. So now he's adding an electron to this oil droplet, and he can levitate by determining what the difference in voltage is. He can levitate that electron. And what he finds out, that he can levitate different electrons that have different numbers of electrons, different numbers of negative charges attached to it. And so he's able to figure out the actual charge of the electron. So J.J. Thomson discovers that it's negatively charged, but it has a charge to mass ratio. Milliken actually determines the charge on the electron, and once he determines the charge of the electron, he can determine the mass of the electron. So Milliken, with his oil drop experiment, is given credit for actually determining the actual coulombic charge of the electron and the actual mass of the electron. So J.J. Thomson, he says, so what we have here, we have a charge to mass ratio. Milliken actually determines the charge. Notice it's a very small number. It's negative, and it is negative, so we know it's negative. 1.6022 times 10 to the negative 19th. And this C here stands for coulombs. And a coulomb is equal to an amp second. So once he notices the charge, and we use Thomson's charge to mass ratio, C to mass ratio, well, the charges cancel out, and the mass comes up to be 9.10 times 10 to the negative 28 grams. So we're talking late 1800s, early 1900s for Milliken to determine the actual charge and mass of the electron. So again, J.J. Thomson discovers the first subatomic particle, the electron, and he knows the charge to mass value, but he doesn't know the actual charge or the actual mass. He knows it's negative, but he doesn't know the actual charge or mass. And Milliken determines that. So we discovered our first subatomic particle. So you go, well, what does that do for me? Why do I need to know this? Well, so the atom's now changed. It's not just a pool ball anymore. It's a sphere that has negative electrons embedded in it, like so. So because J.J. Thomson was an Englishman, we call this the Plum pudding model. So if you hear somebody talk about the Plum pudding model of the atom, the electrons are like raisins embedded in a cake. And so the talk back then was the cake must be positively charged, and then the electrons are negatively charged, and that's why an atom's neutral. So that's what they believed in the early 1900s. So to investigate the atom more, we had to use radioactive materials. So here's what radioactivity is. If we have a radioactive substance that's surrounded by a lead block and we direct the radiation into a beam, we find there are three types of ionizing radiation. And this is the type of radiation we're worried about. This is what causes cancers and things like that. So one beam of radiation bends towards the positive plate here. It's negatively charged, and it's called a beta ray or beta particle. It's a high energy electron. The beam splits and another beam goes down towards the negative plate. That's called an alpha particle. We know that it's positively charged because that's why it's attracted to this negative charged plate. And then one type of radiation, it's neutral because it's not positive or negative. It's not affected by the positive or negative charge plates. It stays in the same trajectory. That's called a gamma ray. The gamma ray has the most penetrating power of these three rays. It does the most damage. It's the most ionizing. Alpha particles have mass. They're kind of like, if you're thinking on the scale, it's kind of like a baseball on the scale that something we're dealing with. It's fairly, if I was throwing a an alpha particle in my hand, it'd probably be about the size of a baseball. All right, and then a beta. Beta is smaller, doesn't have as much mass. This alpha particle, it's actually similar to a 4,2 helium atom, and we'll talk about what that is coming up. But it's actually got some mass, and it's actually got quite a bit of charge. It's 2 positive. But alpha rays are easy to stop. You can stop them with plexiglass or paper, things like that. So you go, why are we talking about this? Well, we needed something small to investigate an atom, and these radioactive particles or these rays are what we're going to use to investigate an atom. So, everybody's thinking, this is what the atom looks like. It's a sphere. We know what the mass of the electrons are, and this is what the atom looks like, the plum pudding model. So along comes Rutherford. So Rutherford, he takes gold, he takes gold and he hammers it so it's so thin that you can see light through it. So it's only a few atoms in thickness. And he places the gold foil in the center of this apparatus. So what this is it's a big band of phosphorus embedded screen or zinc sulfide screen. And so again, if energy hits this sulfide screen, it glows white, and if there's no energy, it just stays dull. And so Rutherford, his hypothesis is, because he knows this is an alpha particle emitter, that this is like throwing a baseball in the air, he expects the baseball has much more mass than anything in this atom over here. So his thought is, if I throw a baseball at this, it's going to go right through it like that. It's going to go right through the screen. No problem, because the alpha particle has mass, much more mass than the electron. And just like when we throw a baseball through the air doesn't stop the baseball from coming back to us. It doesn't knock the baseball back to us. The baseball reflects back to us when it hits the wall. When it hits something more massive than itself, so here's my wall here. So when I throw a baseball, yeah, it sinks like this due to gravity, but it doesn't reflect back until it hits something more massive than the baseball itself. So Rutherford, knowing the alpha particle is much heavier than an electron, he expects the alpha particle to go straight through this aluminum foil, and this is the only dot he should see of energy. So when he does this experiment, he sees something different. So his hypothesis is actually it's actually not what he thought, because what he sees, let me see, I'm missing my let me go over here. Let me I was drawing. Okay, here we are. So let me erase this. I want to erase all of this here. All right, so what Rutherford sees, let's use something a little finer lined here. Yes, this is the brightest spot. Straight in line. This is the brightest energy. But he sees faint little signs here and here. So that means the alpha particle was deflected, not reflected, deflected. And what that looks like is this one here. It glances off some solid center in the middle of the atom and bounces off like that. That's deflection. So that's what we're seeing here and here. Most of the alpha particles go straight through undisturbed. That's why this is still the brightest light. But you also see some reflected. That means they hit the center of something solid in that atom. So much solid, so heavy, that it knocked the alpha particle backwards, changed the trajectory completely. So the atom now changes. Rutherford says, hey, there's something in this atom that is heavier, has more mass than an alpha particle. And so he is the one who gives us the nuclear model the nuclear model of the atom. Nuclear meaning there's a nucleus, a solid center, and in that center he says, okay, there's a positive proton in there. And everybody's happy because now if you have 6 negative electrons, you must have 6 positive protons, and that's why the atom's neutral. It's no longer about some cake batter that's positively charged and the negative electrons embedded in it. It's there's 6 electrons negatively charged, and there's 6 protons in the center of the atom that have mass, that when we add the electrons and protons together, we get 0. We get a neutral atom. Now, the one thing Rutherford's model didn't quite figure out was that not all the mass of the atom was accounted for, and actually one of Rutherford's graduate students determines there's another particle in the nucleus called a neutron. And it was hard to find because it doesn't have a positive or negative charge. It's neutral. So our model really changes here. What we see is, yes, there is mostly empty space in an atom. Empty space where the electron resides. But in the center of the atom, there's a nucleus that is where the protons and neutrons are contained. And that's where the majority, 99+% of the mass of the atom is located. So yes, most of the alpha particles went through, no problem. That's why this was the brightest white light. And that tells us there's a lot of empty space between each solid center nucleus. But there is a nucleus, and it has positive and negative charges, protons and neutrons in them. All right, so the nuclear model, protons and neutrons. All right, so we got a nucleus. There's a new word that came out of this. It's the central core of the atom, and that's where the protons are, and we find out that that's also where the neutrons are. And there it is. Chadwick's experiments determined there's another subatomic particle in the nucleus called the neutron. It was hard to determine because it was neutral in charge, but it helped us determine why, if we just looked at the protons and the electrons, the mass of the atom wasn't working out. So now that we have protons plus neutrons, the mass of the atom starts to work out there. All right, so here's what it looks like. Here's the picture. And I know I'm exaggerating a little bit, but if you want to think about it, it's like you got a softball in the middle of Lexington. Out here to New Circle Road is the edge of the atom. Think of all that space in between the nucleus and the outer edge of the atom for things to move through. And, so there's a lot of space between the nucleus of this atom and the nucleus of the next atom up here. Inside that nucleus, this is what we could see if you could see it under a microscope. We can't, but this is what it would look like. You would have neutrons that are neutral in charge. So there's no charge here, here, here. And then you'd have the positive charge protons. So again, no charge on the neutrons, positive charge on the protons, and then the negative electrons are out here somewhere. All right? So notice how atomic theories changed. So again, theories are human interpretations. We determine theories based on laws. But we've gone from a solid pool ball to a pool ball that has electrons dispersed in it to a nuclear model where we have a solid center of protons and neutrons, and the electrons are somewhere around the nucleus. So there's 3 atomic theories. 1, 2, 3. And we're going to see this theory change even more as we get into chapter 6. So I don't want you to memorize this. I just want you to, this is what I want you to know about this chart here. if you look at this, this is almost 10. So let's just make that 1 times 10 to the negative 27, since this is pretty close to 10. So what you want to look at is from here to here, the size of a proton versus, or the mass of a proton versus the mass of the electron. This is the mass of the electron. It's over 1,000. It's over 1,000 times heavier. This has 1,000 times more mass than an electron. And notice the proton and the neutron have the same mass. So these are equivalent in mass, and they're both 1,000 times heavier than an electron. So a lot of times we talk about the electron's mass being negligible, because think about this. You know, we were talking about adding exponents together. We're trying to add this to that. So you would have to have 0.0001 to make this times 10 to the negative 24th power to add it to this. So the first digit's only going to affect this place as far as mass goes. So that's why we say the mass of the electron is negligible compared to the mass of the proton and the neutron. Now, this next column, if you're taking advanced chemistry or physics, a lot of times physics wants to know what is the actual charge of the electron, what is the actual charge of the proton, in a unit called coulombs. For us, we don't really deal with the coulombs till a little bit later, not in chemistry 170 at all, maybe in the end of Chem 180. But what we say is an electron is a -1 charge and a proton's a +1 charge and a neutron is 0. So these are called charge units. So don't ever say that the electron is -1. That's the charge unit of the electron. And that's good enough for us. But these are the actual charges in coulombs. These are just unit charges. So what's a unit charge? If I divide this number by this number, I get that number. It's a unit charge. It's not the actual charge. So just keep that in mind. That's what I want to stress on this slide here. It makes it easier for us in chemistry to think in terms of unit charges. All right, atomic number, mass number, isotope. You need to be able to define each of these, be able to locate them in an atom, be able to write a isotopic symbol that represents atomic number, mass number, and isotopes. So the atomic number is the number of protons in the nucleus, and it's given the symbol capital Z. All right, so you need to know that. Capital Z, we're going to see this again later on. So Z represents the number of protons in the atom that makes up the element. Mass number is given the symbol capital A. So the mass number is equal to the number of protons and the number of neutrons. So we add the number of protons to the number of neutrons and we get the mass number, which is capital A. And you go, why do I need to know that? Well, what you're really going to use the most is the mass number minus the atomic number gives you the number of neutrons. You're probably going to use that the most. And that's the way we would write it. It's easier to write that than to write all of this or all of this or all of this. So know that capital A is the mass number. And here's what I want you to remember about the mass number. It's a counted number. It is a whole number. It is the number of protons and neutrons in the nucleus. You don't have 1.5 protons. You either have a proton or you don't. And the atomic number is just the number of protons. So the mass number, which is protons plus neutrons, minus the atomic number, which is the protons. These subtract out and you're left with neutrons. So that's why we use this equation. So we have to have a compact way of writing this symbol, and that's called an isotopic symbol. So an isotopic symbol has these elements in it. First of all, you have the elemental symbol that you get from the periodic table. So in the case down here, we have hydrogen. That's the elemental symbol for hydrogen. In the lower left-hand corner, you have the atomic number, which is the number of protons. And you say, where do I get that? Well, it's on the periodic table. If you look on the periodic table, you'll see a hydrogen, and you'll see a number 1 up here somewhere or something like that. That is its atomic number. It is the number of protons in the hydrogen atom. The mass number is equal to the number of protons and neutrons in the hydrogen. Now, here's where Dalton made a mistake. So Dalton said all atoms of a particular element are exactly the same. They're identical. Well, we find out that when we gather hydrogen in the universe and we run it through a mass spectrometer, we find out there are 3 types of hydrogen atoms. There's this hydrogen, there's this hydrogen, and there's this hydrogen. Now, chemically, they do behave exactly the same. Can't tell the difference chemically. So that part Dalton got right. Chemically, they're exactly the same. But look at the mass here. This particular hydrogen, sometimes called protium, because it's the first, it only has 1 proton. It has 0 neutrons. You go, how do you know it's 0 neutrons? Because if I take the mass number, which is 1, minus the atomic number, which is 1, I get 0. So remember that A minus Z equals neutrons? Here it is. A minus Z equals 0. So there's no neutrons in protium. Now, deuterium, it's called deuterium, means 2, mass number 2. So if I take 2, the mass number, minus 1, the number of protons, I get 1. So deuterium has 1 neutron. And you say, why do I need to know this? Well, let's say your body had deuterium water in it instead of hydrogen water. Instead of H2O in your body, you would have D2O in your body. So tell me physically, what would that do to your body? Chemically, it's the same. You can't tell any difference between water and deuterium water. But what would that do physically to you? Think about it. Hit pause if you can't pop an answer right off, but once you hit pause and think about it, I hope you come up with the answer that you'd weigh twice as much. This one has twice as much mass as the protium. Deuterium has twice as much mass. Because it's got a proton and neutron, they both weigh the same, right? So it's twice as heavy. They got the same number of electrons. And then we got tritium. It's got a mass number of 3, 3 minus 1, it's got 2 neutrons. It's 3 times heavier than protium. It's so heavy that generally when atoms get really heavy like that in the nucleus, they fall apart. They're radioactive. So tritium is actually radioactive. And you go, will I ever see that? Well, if you have a watch that the markers glow in the dark all the time, they don't need to be recharged. There's probably little tritium dope markers. Or if you have night sights that on a gun that glow all the time, they don't need to be held out in the sun. They probably have tritium markers on them. So that's where you see tritium. It's an energy source used to energize phosphorescence in your markers on a watch or a gun sight. So Dalton got this part wrong, but we're okay. That's what happens when we have theories. Remember, theories change. Theories change. As we gain more knowledge, theories change. And so what we have here are 3 isotopes. That's the name, and you need to know that name. 3 isotopes of hydrogen. They all behave chemically the same, but they do have different masses. So again, when you're going through the chapter and you see something in bold, write that down. Write that down in your journal so you can speak the language of a chemist and actually a physicist here. This is mostly physics, right? So isotopes. There are 3 isotopes of hydrogen. Now, you go, why do I need to know this? Well, if you look on the periodic table, you'll find out that hydrogen weighs 1.00794. What does that mean? it's not grams. We know it's not grams because we just saw that the mass of a proton and neutron was like 10 to the negative 24, 10 to the negative 24 grams for a proton neutron, 10 to the negative 28 for an electron. So this is AMUs. That's the unit of mass that we're going to be dealing with on the periodic table. And what we're going to find out is 1 proton is equal to 1 AMU, approximately. Let's say approximately here. And I'm not liking that pen very well. Let's go back to the black. And 1 neutron, because it weighs the same as a proton in grams, 1 neutron weighs approximately 1 AMU. So this hydrogen weighs 1 AMU. It's got only 1 proton in it. This hydrogen weighs 2 atomic mass units because it has a proton and a neutron. And this one weighs 3 atomic mass units. But you notice the average up here is really close to 1, much closer to 1 than it is 2 or 3. That tells us this hydrogen is the one that occurs the most in nature. That's where we're going with this. That's why you need to know about isotopes. And we're going to use isotopic masses, the individual masses of these isotopes, times the percent they occur in nature. We call it relative abundance, to figure out the average that you see up here that's on the periodic table. So that's where we're going with it. That's why isotopes are important to us at this point. All right, so one of these uraniums is energy grade uranium. One of them's weapons grade uranium. They're both uranium. How do we know they're uranium? They have the same atomic number, the same number of protons. The protons define the element. As soon as you say 92, I know that's the symbol that I need to use. But the difference between these two uranium atoms is when I take A minus Z to find out the number of neutrons, this one has 143, this has 146. Mass number minus the atomic number gives us the number of neutrons. They weigh different amounts. This one's heavier than this one. This one has the ability to release more neutrons than this one, which is important in some reactions. So, I want you to be able to answer this question. So we have isotopic symbols, and then we have isotope speak here as the last one. I want you to be able to tell me the number of protons, neutrons, and electrons in each one of these isotopes, in each one of these atoms. All right? So, stop the video, write down your answers, and then turn the video back on. Now, before you do that, let me just say this. This speak here that we're talking about, carbon tells us the symbol, and the 14 tells us the mass number. It has to be the mass number because the atomic number for carbon is 6. All right? So when you hear the word carbon 14, it's the element, and the 14 represents the mass number, or hydrogen 3 or something like that. Remember that it's the speaking of it, that's the way we would say it. We would call this chlorine 35, we call this chlorine 37, we call this potassium 41. So the speaking of it. All right, so stop the video, write your answers down, tell me the number of protons and neutrons in each one of these, and then let's get back to it. Well, okay, let's get through this. I thought they would show the... So, the first one, atomic number 17, that defines chlorine. So we had chlorine defined by the atomic number 17. We have a mass number of 35. So 35 minus 17, we got 18 neutrons. So 18 neutrons. So the way I'd write this is, how many protons? 17. How many neutrons? 18. How many electrons? It's got to be the same number as protons. So protons, neutrons, electrons. Now, read the question carefully when you're doing your homework, because instead of protons, neutrons, and electrons, it might be protons, electrons, neutrons. You got to see what the order is. But again, easy to find. Atomic number, A minus Z gives me the neutrons, and whatever the number of protons is, that's what the electrons have to be if the atom is neutral. Always has to be the same if the atom is neutral. All right, the next one, we got chlorine 37. So 37 is the mass number. 17 is defining chlorine. That's the number of protons. So this one has 20 neutrons. How many electrons does it have? It has to have the same as the number of protons to be neutral. So 17 electrons. So protons 17, neutrons 20, and electrons 17. So that's what we're saying. Isotopes, chemically they're the same. Chemically they behave exactly the same because they got the same number of electrons. Mass-wise they're different. All right, potassium 19. Notice they didn't give us the atomic number. You have to look that up on a periodic table. So if you look on the periodic table, potassium is number. Atomic number. Oh yeah, they said it was. Yeah, I did that wrong. They said it was potassium 41. Let's make sure they did that right there. I'm getting. Yeah, okay. It's called potassium 41. That's right, potassium 41. All right. So potassium 41, they don't give you the atomic number. You have to look that up on the periodic table. It's 19. So 41 minus 19 tells me the number of neutrons, 22. So protons is 19, neutrons 22, electrons are what? You should have the same number of electrons as you have protons. And then the last one, carbon 14. We know that it has an atomic number of 6 when we look on the periodic table. It's got 8 neutrons. 14 minus 6, 8 neutrons, 6 protons, and we've got to have 6 electrons for it to be neutral. All right, periodic table. So what you want to do for this section is you want to go into Blackboard, click on the periodic table button on the left sidebar in Blackboard, and print you off a table. Now, you can write on this table all you want to that's just for practice getting ready for the exam. But when you take the exam, you have to have a clean copy of the periodic table, nothing written on it, just the periodic table as you see it in Blackboard. But it's okay to print one off now and write things down that we're going to talk about on the periodic table here so that you can learn all the different regions and what the columns mean and the rows mean and so forth. So print off a periodic table and then so stop the video, go print off a periodic table, then come back and let's start marking up the periodic table. So right off the bat, periodic means cyclical property. That means as we go through the table, we see patterns. The periodic table is like the chemist's dictionary. There's so much information embedded in the periodic table, and you should always have one present on any chemistry exam. It's a requirement. If somebody doesn't give you a periodic table, you should throw a fit because it's required so that you can pull information out of it. Otherwise, it'd be too much to memorize. So the periodic table, this one's been enhanced, and it's again the one in your Blackboard shell has not been. So why did they enhance this one? Well, this one's enhanced to show that anything that's in green here is a metal. So all these are metals, everything in green, all this is metals. Anything in blue is a non-metal. I'm just going to say NM. And the ones that are along this stair step here, you're going to hear the word stair step a lot. And it's marked in red on your periodic table. Now, the one that's on the wall in the classroom doesn't have that marking. anything along the stair step that's touching the stair step except aluminum on a side is considered a metalloid. It has some of the properties of metal and it has some of the properties of a nonmetal. And it's important to distinguish the metalloids because if you notice, most of these are what we use in computer chips and CD lasers and so forth. So that's why they're important. So green is metals. Everything to the left of the stair step is a metal. Everything to the right of the stair step is a nonmetal, and anything touching the stair step is a metalloid. You need to know that. Now, the one that throws people the most, hydrogen's way over here. It's a nonmetal. It is a nonmetal. It should be over here. In fact, some periodic tables put a hydrogen right there to show that it's a nonmetal and it's similar. It's got some properties like the group 17 here. So just remember, hydrogen is a nonmetal, even though it's far to the left over here, because the stair step starts here. All right, so this is above the stair step. This is a nonmetal. All right, so on the periodic table, we have elements that are arranged in horizontal rows called periods. And then we also see vertical columns called groups or families. I want to use the word groups. Some biologists use families still, but groups is the more preferred term. So groups and periods is what I'm going to use. So every element in a vertical column, called a group, tend to have similar physical and chemical properties. So for example, lithium, potassium, sodium all have similar chemical properties. On the other side, fluorine, chlorine, bromine have similar chemical properties. They're in vertical columns called groups. We're going to find out why that's the case here in a few slides, or a few slides. All right. We've seen the categorizations: metals, nonmetals, or metalloids. You need to know where those are. So there must be differences between metals, nonmetals, and metalloids. Otherwise, we wouldn't be able to distinguish. We wouldn't be able to put those strong dividing lines between them. So metals are good conductors of heat and electricity. You know that. They are shiny. Shiny? I never can spell this right. I mean, really, after all these, I won't say that. All right. So they're shiny. A fancy word is lustrous. I think I can spell that better. Let's say lustrous. They're malleable, which means that you can hammer them out into thin sheets. So you can make foils out of the metal. Whereas a non-metal, like a piece of charcoal, if you try to hammer on a piece of charcoal, it just breaks up into a powder. So non-metals tend to be brittle. That's the opposite of malleable, kind of, right? Non-metals are poor conductors of heat and electricity, so they're used as insulators usually. So think about fiberglass insulation. It's mostly non-metals, mostly carbon, hydrogen, some other non-metal compounds. What else? Oh, metals are ductile. That still kind of goes with the brittle. Ductile means you can pull them and make wire out of them, that you can clamp on two pieces of a block of metal and extrude it, pull it into wire. So these two kind of go hand in hand with the opposite of brittle. So keep those in mind. And then your metalloid, like silicon, it can conduct electricity. So it conducts electricity, but it is brittle. So that's why a computer chip is always put in some little socket, so if you drop it, it doesn't just fracture it all to pieces. But you know, if you leave your computer in a car and it gets really cold at night, and then you bring it inside when it's hot, just the shock of the temperature change can break those little silicon wires, and they can damage your computer or your calculator. Or if you keep dropping your calculator or your computer or your cell phone, it might start acting a little wonky because you started to damage the connections in there. So metalloids, they generally conduct, what we like about them is they generally conduct electricity, but they are brittle, but they are lighter than metals, and we can make really small wires out of them, and that's why they're great for semiconductors and chips. Know where the dividing line is, know the properties that distinguish a metal from a nonmetal and a metalloid. All right, some groups are so important to know that we use them so much that they got their own names. So the first group is called the Alkali Metals. The second group is called the Alkaline Earth Metals. Alkali means base, strong base. Alkaline earth, these are still basic from the earth metals. Then from, I call this tower, this is the first tower here, and over here is the second tower. So between the first tower and the second tower is all of this. These are the transition metals. Transition. So what is a bridge? A bridge is a transition between two land masses. So you got this mass over here, Tower 1. You got this mass over here, Tower 2. And the transition metals are the bridge between the two towers. Notice it's indented. I mean, it's indented. It's not up here. It's down here. Both of these towers are taller. They loom over the bridge here. This group is called the chalcogens. This is group 16 on your periodic table. It's got oxygen. It's got sulfur. Generally, when these react, they form chalky materials, things like that. Then we have the halogens. That's really important, group 17. And then we have the noble gases, group 18 here. So you need to know the names of those groups, those vertical columns. Every element that's in a group has similar chemical and physical properties. Every element in a group has similar chemical and physical properties. All right, so the next thing we notice on the periodic table is the atomic masses that we've talked about. We've said that, you know, hydrogen has a mass of 1.00794. What does that mean? Where does it come from, and so forth? That's what this section is going to be about. All right, so what I would say is maybe you're tired of hearing me talk. You can always stop these videos and come back later. I just decided to record 2 1-hour and 40-minute videos just to knock out the classes, but you don't have to listen to it all. I understand that. I wouldn't want to listen to this for 1 hour and 40 minutes either. So you may want to stop here, or you may want to stop before the periodic table and then, you know, come back to it. You don't have to do it all in one setting. All right, so what are we doing? The question is, what is atomic mass scale and what is the average atomic mass? That's what we're going to learn in this section. So by when we end this, we should know. All right, so the first thing to know is that all elements on the periodic table are relative to one isotope of carbon called carbon-12. That's carbon with a mass number of 12, has an atomic number of 6. So we saw that the mass of a proton is 10 to the negative 24th grams, mass of electrons 10 to the negative 28th grams. Nobody wants to work with numbers like that. We want to work with nice whole numbers. And we want low numbers, 1, 2, 3, 4. So what we're doing here is, let's say a person weighs 100 pounds, 150 pounds, 200 pounds, and we'll say 300 pounds, all right? Something like that. Instead of having this big range of mass, or weight in this case, let's say we make everybody's weight relative to the person who weighs 100 pounds. So what that means is I'm going to divide everybody's weight by the 100-pound weight. And by doing that, that makes this number 1, this is 1.5, this is 2, and this is 3. Much more manageable numbers. I'd rather work with these numbers than these numbers any day. So all masses on the periodic table are relative to one atom of carbon-12. And so what we do is we say, here's the big thing. One atom of carbon-12 weighs exactly, this is by definition, this is an exact number, one atom of carbon-12 weighs exactly 1 atomic mass unit. And you can say 1.0 out to infinity. But that's what we define as atomic mass unit. One atom of carbon-12 weighs exactly 1 atomic mass unit. So you saw in the previous slide I said that a proton is approximately equal to 1 atomic mass unit and a neutron is equal to approximately 1 atomic mass unit. Where we get that is in carbon-12 you have 6 protons, you have 6 neutrons, and the mass of the electrons are negligible compared to a proton-neutron. And we know that the proton-neutron weigh the same in grams, so each one of these protons is 1 atomic mass unit, and each neutron is 1 atomic mass unit. If we add those together, we get 12 atomic mass units, and that is the definition that, oops, I said this wrong up here. One atom of carbon-12 weighs 12 atomic mass units. I made a mistake right there. One atom of carbon-12 weighs exactly 12 atomic mass units. So, we add this all up, we get 12 atomic mass units. So, one atom of carbon-12 weighs exactly 12 atomic mass units. Or, another way to say it, and that's what this says up here, 1/12 of a carbon-12 atom weighs 1 atomic mass unit. So I like this one better I like this thought better just because I see now where the 1 proton equals 1 atomic mass unit and 1 neutron equals 1 atomic mass unit comes from. But either way it works. All right? So all elements on the periodic table are relative to carbon-12 so that we have a much more manageable numbers to work with. Not exponents like 10 to the negative 24th grams. All right, so what we know is this. We know that experiments have shown that hydrogen 1, called protium, is 8.3985% as massive as a carbon-12 atom. So if we multiply the percentage as a decimal form, so we've taken this number here and divided it by 100, and we multiply the decimal form of this number by the 12 atomic mass units that we defined as one atom of carbon-12, we find out that an atom of hydrogen has an average atomic mass of 1.0078, which matches what we see on the periodic table. So that's the way it works. Everything is based relative to carbon-12, and the percentage of that mass for that element multiplied by the 12 atomic mass units. All right? So that leads the question to, well, when I look on the periodic table at carbon, the atomic mass for carbon on the periodic table is not 12. It's 12.011. What does that tell you? Well, that tells you there's more than one isotope of carbon. There's carbon-12, and then there must be a carbon that's heavier than carbon-12. That's why this is 0.011. Well, it turns out there's another form of carbon called carbon-14. All right, so what we do is we get a sample of carbon, we run it through a mass spectrometer, and we find out there are 2 isotopes of carbon, carbon-12, carbon-14. Carbon-12 occurs 98.93% of the time. That's called its percent relative abundance. 98.93% of the time, or by mass, the carbon is carbon-12. And so if we subtract that from 100, and actually there's some other ones, but here we get this one, 1.07% of the time, it's carbon-14. If we divide that by 100, we get this number. So carbon-12 weighs exactly 12.00 out to infinity. That's the definition of carbon-12. Carbon-14 actually weighs 13. You say, well, wait, how does carbon-14, you just told me that a proton weighs 1 atomic mass unit, and you said a neutron weighs 1 atomic mass unit, so why doesn't this weigh 14 instead of 13? Well, here's something we found out later, and that is, as there's more protons and neutrons in the nucleus, in this case more neutrons, protons are fixed. As there's more neutrons in the nucleus, it takes more energy to keep the nucleus together, to hold it together. So some of the mass of the proton and neutron in atoms heavier than carbon is converted to nuclear binding energy to hold the nucleus together. So that's why carbon-14 weighs less than 14. It weighs 13.003355. So if I take this decimal form of relative abundance and I multiply it by the mass of the isotope for carbon-12, do the same thing for carbon-14, and I add those together, I get the average atomic mass that we see on the periodic table to 4 significant figures. So that's where these numbers come from. And the more digits you see after the decimal, the more precise we know the isotopes and how much they occur in nature. For things like lead, that is, the average atomic mass is 207.2. That's not very high precision, right? That tells us something's going on. That there's lots of isotopes, or that the isotopic percent relative abundance changes as we go around the Earth or something. Different deposits of lead have different isotopic mixtures. So the more digits you have after the decimal, the more precise we know the atomic mass of that substance. Some people do call it atomic weight. I'd like you not to use that term. It's an older term. We're going to call it atomic mass, average atomic mass, or atomic mass for short. So you go, well, what am I supposed to get out of this? Well, you're supposed to be able to do a problem that's coming up. But before we do a problem that's coming up, let's look at, this is what I'm talking about, how we separate isotopes. So we take neon gas, we pump it in here. As the gas goes through this filament here, electrons are added to the gas, and that makes it charged. So then it's accelerated to these positively charged plates, which makes it speed up. And there's a slit in the plate to culminate the beam into one column. And then we pass it through this magnetic field, and what we find is the lighter the element is, or the heavier the element, the more it doesn't change. It stays in the same path. But the lighter the element is, or the heavier the element is, it starts to deviate from the path. It interacts with this magnetic field. The way to think of this is, you got a curve here in the road. You got a massive semi coming this way, and you got a little car going this way. When we hit the curve, the mass of the semi wants to go straight like this. The lighter car can make the turn. It's easier for it to change direction than the inertia that's built in this semi. So now we've separated the lighter from the heavier. So when this hits the detector back here, we get peaks. And so here is neon 20, neon 21, neon 22. So there's 3 isotopes of neon, and we can quantify how much area is under this curve. We find out that 90.48% of the isotope that's abundant, the relative abundance, is neon 20. 0.27% is neon 21, 9.25% is neon 22. So that's how we figure using mass spectroscopy, called MS for short. This is how we determine how many isotopes there are of a particular element, and we determine the percent relative abundance of each, or we just call it relative abundance. We convert those percentages into decimal forms and multiply it by the mass of each of the isotopes. When we add those together, we get the average atomic mass. Now you say, I'm lost. I'm totally lost. Okay, well, let's look at a problem. Okay, let's look at a problem here. So oxygen is the most abundant element on Earth's crust and in the human body. And oxygen comes in three isotopes: oxygen 16, oxygen 17, oxygen 18. So we take oxygen, we pass it through a mass spec, just like we did the neon, and we're going to get three peaks. We're going to get oxygen 18, oxygen 19, oxygen 16, or whatever, 16, 17, and 18. All right. So when we pass it through the mass spec, we find out that 99.75% of the oxygen that occurs on the Earth is oxygen 16. 0.038% is oxygen 17, and 0.205% is oxygen 18. And then here are the masses of each of the isotopes. For oxygen 16, it's 15.9949. Yep, it's a little less than 16 because oxygen is heavier than carbon. So some of the mass of the protons and neutrons in oxygen are converted to nuclear binding energy. Oxygen 17 is a little bit less than 16, and oxygen 18 is a little bit less than 18. It's a little less. Oxygen 18 is the mass of it's a little less than 18, right? Okay. So right off the bat, you know this one occurs the most in nature. How do you know? Because when you look on the periodic table, the average atomic mass for oxygen is 15.99994. So that tells me that oxygen 17 doesn't occur very much in nature, nor does oxygen 18. But I want to find the average. So what do? I take this percent relative abundance, divide by 100, make it a decimal, and then multiply by its mass. Do the same thing here. Take the 0.038%, divide by 100, multiply by its mass. Divide the 0.205 by 100, multiply by its mass, add those up, and I will get the average atomic mass for oxygen. All right? So let's look at the next slide. That's what we have here. We've taken the percentage, divide by 100, get the decimal form, multiply by the mass of that particular isotope. Do that for each one. This is oxygen 16, oxygen 17, oxygen 18. And when we add those all together, we get an average of 16.00. And if you look on the periodic table, if you look at 15.999, it would round up to 16.00. So that's how we come up with the masses that you see on the periodic table. The more digits past the decimal, the more precise we know the measurement. The less digits past the decimal, the less precise we know. And it generally comes about by these percentages are not constant where we're sampling throughout the Earth. All right, section 2.6. This is where you're going to have a lot of memorization. You're going to have to make some flashcards, and I want you to memorize the things I'm going to talk about here. I'll tell you what you have to memorize, but you have to speak the language of a chemist. You have to know if somebody says, go pick me up some ammonium nitrate, that you know that it's NH4NO3, and you don't have to look it up. So, to me, the hurdles in this class is, first of all, the math. If you get through the math, this is the next hurdle. You have to do the memorization here. Now, if you've got a couple of weeks to memorize this stuff, if you look at this video on Monday, you've got another week and then the test. So The main thing to do here is just make you some flashcards. So what you're going to do on a flashcard, on one side of the card, you're going to put NH4 positive. It's called a polyatomic ion. And on the other side, you're going to put the name of it, which is called the, I don't have enough space here, ammonium ion. Ammonium, not ammonia, ammonium ion. All right? There's no getting around this. You have to do it. You're going to have a lab on it coming up. It's just at the labs later on the semester because we can't get the naming and so forth to bond together because different people are teaching different ways. So you're going to have naming on this exam. You're going to have it on the midterm. If you don't know naming by the final, it's all going to fall apart. You're going to have naming as one of the labs if you're taking a lab. It's also one of the spotlight sessions. That's how important this section is. All right, so the first thing we have to know is what's the difference between an atom and an ion. So an ion is a charged atom. And the way we make a charged atom is we can't change the protons. We cannot change the protons. All you can do is change the electrons. So in a neutral atom, you would have 11 protons in sodium because it has an atomic number 11. If we take one of the electrons away, it becomes a positive sodium ion. And you say, well, why would it do that? Well, sodium is in group 1 on the periodic table, and everything in group 1, all you have to know, you don't have to know why it happens yet. All you need to do is memorize, and this is why you want your periodic table out. Every element in the first vertical column, the first group, forms a positive 1 ion when given the opportunity. Positive 1. How does it form a positive 1? It loses an electron. So now we have 10 electrons, 11 positive protons. The overall charge now is a positive 1 charge. A positive ion is called a cation. You need to know the terminology. That's easy to remember. That looks like a T, right? In cation, so sodium is a cation. Net positive charge. Metals tend to form positive ions. So that's why you need to know the periodic table and where the metals are located. Metals form positive ions. Nonmetals, like chlorine, is in group 17. So the nonmetals are on the right-hand side of the periodic table. We have fluorine, we have chlorine, we have bromine. Normally, chlorine would have 17 protons, 17 protons and 17 electrons. Yeah, let's do it that way. It'd be neutral, and it would be called chlorine. But chlorine, being a nonmetal, gains an electron. Things on the right-hand side of the periodic table, the nonmetals tend to gain electrons. Everything in group 17 generally forms a negative 1 ion. So just memorize that or put that at the top of your group. Group 17 forms negative 1 ions in general. Negative ions are called anions. Anti, anion, negative. All right? So opposites attract. So ionic compounds is when positive ions like sodium come in contact with negative ions like chloride. Notice the name change. Once this gains an electron, it's no longer called chlorine, it's called chloride, IDE. Chlorine is highly reactive. If you breathe this, it forms hydrochloric acid in your lungs. Chloride you swallow every day in the form of table salt. So, chloride has totally different chemical and physical properties than chlorine. Why? Just because of that extra electron. But when a positive ion comes in contact with a negative ion, we form an ionic compound that consists of a cation, sodium, and an anion, chlorine. And they combine in such a way that when we add these two charges together, it equals 0. It's neutral. So keep that in mind. That when you add the charges together, it should come out to be neutral for a neutral compound, for a compound that doesn't have charge with it. That's where we're going with this. This is how we're going to get the naming down. So this periodic table, you want to memorize what the what the charges are for each one of these groups. So notice this, we could just say this is all +1. This is all +2. Don't worry about these yet. The nonmetals, they gain electrons. So group 15 nonmetals, they want to gain 3 electrons. So these form -3 ions, group 16 forms -2 ions, and group 17 forms -1 ions. Now, if you know anything about this, what it is, this 5 combines with this 3 to make 8. 6 combines with 2 to make 8. 7 combines with 1 to make 8. These over here, they lose electrons to have a full outer shell bake. Now, we're going to talk about that later. If you don't know that, that's okay. At this point, all you need to do is memorize group 1's +1, group 2 is +2, group 15, or 5A is 3 negative, 6A is 2 negative, or 16, and 17 is 1 negative. And then I'll talk about these in a minute, but that's what you need to know. And again, this being a metal in group 13, 3A, forms a 3 positive. It's a metal. Metals lose electrons, nonmetals gain electrons. So spend a little time on this chart here and memorize these. It's going to make it so much easier for you. If you don't get this part down, I think it's where it starts to fall apart. Now, let me just talk about the transition metals. The transition metals are the hardest because they come in multiple charge states. And I'm going to ask you to memorize some of these because they're so important. Iron's one of them. Copper, I want you to memorize those. Mercury, tin, and lead. Now, tin and lead, that's easy because they're both in the same group. So they're both in group 14, and you would expect them as metals to form +4 ions. But they also form a +2. So these 5 metal ions that are polyvalent, that's what I call them, polyvalent, because they're more than one charge form. You need to memorize those 5. I'm not asking you to memorize all of them, just these 5. And the reason why is because you hear about mercury in fish, you hear about lead in drinking water. If you brush your teeth with Crest toothpaste, there's a substance called stannous fluoride. Copper is used as a bactericide, and then iron, we have different types of rust. And so there's iron 2 oxide and iron 3 oxide, and they come up over and over again. So that's why I want you to memorize those 5. And I've got another video on naming, and I'll post it to help you learn how to name. All right. Now, I didn't ask you to memorize manganese, but I do expect you to know this. If manganese is in the transition metals, let's go back and look at manganese. I'm not asking you to memorize this, but this is what I expect you to be able to do. You look at manganese and you go, oh, it's a transition metal. Transition metals tend to have multiple charges. So if I give you the charges or I give you the name, you ought to be able to interpret that. So according to the stock system, make sure you understand stock system. That's called the new system, but we call it technically the stock system. Whatever the charge is on the ion, use a Roman numeral to represent that charge. So manganese with the 2 positive charge is called manganese Roman numeral 2. Manganese 3 positive is manganese Roman numeral 3. Manganese 4 positive, manganese Roman numeral 4. So we like this method the best. This is the method. I wish everybody would use this method, but if you're a pharmacist, they still use the old system. I think it's starting to change, but it hasn't changed yet. So those 5 I've asked you to memorize. We're going to know the new system, the stock system, and we're also going to know the old system because they still use the old system in a lot of consumer goods. So if somebody says cobalt Roman numeral 3, ion, I expect you to say that's cobalt with a 3 positive charge. That's not memorization. That is, you know that Roman numeral represents the charge on the ion. Or if I give you this ion, you can write the stock system name for it. Okay, so this is one of the ones I asked you to memorize, the 5. And here's what happens. I expect you to look at that, and as I said, what's the stock name for this? You would say this is iron Roman numeral 2 ion. That's the stock name, or the new name. You would say this is iron Roman numeral 3 ion. So this is the stock system. The old system, which is still used today, the lower charge form gets the OUS ending, and the higher charge form gets the IC ending. Now that's what makes this hard, because in copper, the lower charge form is positive 1, not positive 2, and the higher charge form is positive 2. So the lower charge form gets the OUS ending, so this is called cuprous, and the higher charge form gets the IC ending, this is called cupric. So 2 positive in iron gets the OUS, 2 positive in copper gets the IC ending. So that's why you have to memorize, actually memorize those particular ions. There's not like a system to it. You have to memorize what's the lower charge form, what's the higher charge form. Now, it'd be great if everybody uses stock system, so maybe you'll change this in your lifetime and just say this is copper Roman numeral 1 and this is copper Roman numeral 2. Much easier, but it hasn't caught on yet completely. And it's been around since before me. All right. So the ones I want you to know, I'll actually post another video and on naming, and you can see the ones I want you to know how to do it. All right, this slide, the main thing is, this is chlorine, this is chloride, totally different chemical and physical properties. This is a gas, this is highly toxic, highly reactive. This you swallow every day in table salt. Still reactive. Some people say it contributes to heart disease, right? Or osmotic pressure differences in your cells. And it does do that. So it does have, but it's nothing like chlorine gas, all right? So to distinguish this, we have an IDE ending for this. This is chlorine, INE. This is chloride. Totally different. That's the way the nonmetals tend to go. The atom is INE or something, whatever, nitrogen, oxygen, chlorine, bromine, iodine, and then the ion has an IDE ending. All right, so here's something you're going to have to memorize. I'm going to point out the ones you need to memorize. This is the polyatomic ions. Polyatomic means more than one atom bonded together with a charge. You definitely need to know that one, that one, that one. That's one of the 5 I've asked you to memorize. Acetate. I don't care about the azide. We can skip that one. Carbonate. There's a typo. Let's see. There's a typo here. This is supposed to be a 3 there. CO3, 2 negative. Yes, you need to know those. We're going to skip the chromate. You need to know the cyanide. You need to know that one, 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 that one. We'll skip the oxalate. This one's named incorrect. Look at that. There's a lot of typos here. This is oxalate. Oxalate. You don't need to know that one. I'm going to let you skip this one, although that one's pretty common in biology. You definitely need to know that one, that one, that one, that one, that one, and I'll let you skip that one there. So you got to memorize these. The only way you can memorize them, get you some flashcards, put the on one side, name on the other. There's no getting around it. You say, well, why do I have to do this? Well, you should have memorized it in high school. They should have made you memorize this in high school, and then it'd make it easier for college. But most people aren't doing that. But here's the deal. There's no way you can be in lab and have to look up every chemical that you're going to be using. You don't have the time. You'll run out of time. You've got to know these by sight. Now, I can help you. There's some tricks. Let me give you a trick here. And in fact, I'll just do one of them, then I'll expect you to watch my video. So, on naming. So, this is called sulfate. If you knock an oxygen off of it, it's called sulfite. So, this is sulfate with an AT ending. This is sulfite with an IT ending. Here's another one. ClO3 negative is chlorate. Knock an oxygen off, it's chlorite. Knock another oxygen off, it's called hypochlorite. That's the active ingredient in bleach. Add an oxygen up here, it's called perchlorate, like hyperchlorate, but we call it perchlorate. I've got a whole video on this, on the naming, and I want you to watch it. You got to watch it along with this, and it'll help you a lot on naming the compounds. But the bottom line is, you've got to get these flashcards going. Flashcards are the only way I know to get this down quickly and do well enough to take an exam on it. All right, so yeah, we've already said this is one to memorize, that one, skip that one, know that one, skip that one, know that one, that one, that one, that one, that one, that one. This one's not a big one to know. Look, if this is sulfate and you add a positive hydrogen to it, hydrogen's in group 1, forms a positive 1 ion, then it's hydrogen sulfate, no big deal. Or the old name is bisulfate means hydrogen attached to a sulfate. So when somebody says bicarbonate, like you know the Armor Hammer baking soda, sodium bicarbonate, well that's sodium ions with a carbonate ion, hydrogen carbonate ion. We just call it bicarbonate, that's the old name for it. And you see it right there. Okay? And by adding a positive, so carbonate is CO3, 2 negative. When we add a positive hydrogen to it, it becomes HCO3, 1 negative. All right? So that's easy. And like I said, I've got a nice video for you to watch on this. Oops. I went too far, didn't I? Okay, next one. Yeah. Nitrate. Knock an oxygen off, nitrite. We'll skip the oxalate. Chlorate, yeah. Peroxide, yes. Phosphate, sulfate. We'll skip the thiocyanate. Again, I will post a naming video to help you here. Why do you need to know the names? Because this is what's going on. Here's sodium, neutral atom, 11 protons, 11 electrons. Here's chlorine, 17 protons, 17 electrons, it's neutral. Sodium being metal, group 1, loses an electron. That electron goes to the chlorine. Sodium now becomes a sodium positive ion. Group 1 atoms become positive 1 charged. Chlorine gains the electron, has now an extra electron compared to protons, and becomes negatively charged. Opposites attract, and they form a bond between them called an ionic bond. And that bond continues to the point that it forms a crystalline solid of repeating chlorines in green and sodiums in white here, or gray, and we get a sodium chloride crystal. So ionic compounds, what happens is you have sodium positive 1, you have chlorine negative 1. They combine 1 to 1 to make sodium chloride. Now, let's do another one. Let's say I want to combine calcium with nitrogen. Calcium's a metal. What's the charge going to be on a calcium ion? Well, you look at the group number. It's in group 2, so it forms a positive 2 ion. Nitrogen is a nonmetal. Nonmetals tend to form anions. It's in group 15. Group 15 tends to form a negative 3 ion. What do 2 and 3 both go into? 6. So, you need 3 calciums. 3 times 2 positive gives you 6. And you need 2 nitrogens. 2 times -3 gives you -6. So that when you have +6 plus a -6, you add those together, you get 0. And for ionic compounds, you want that to come out to be neutral, unless it says it's a charged substance. All right? So the reason why I like this method of coming up with the answer, let me give you another one that throws a lot of students. Let's say I want to know what the chemical formula for stannic sulfide is. Stannic sulfide. All right? So what I expect you to do is you got 10 memorized, and the higher charge form of 10 is 4 positive. That's going to get the ic ending. The sulfur is a nonmetal, group 16. It forms a -2 ion. So I have seen students that learned in high school to do this crisscross method, and they would say, well, this 2 from here goes with the 10, and the 4 with the 10 goes to the sulfur, and they say, there's my chemical formula. Well, that's the incorrect chemical formula for stannic sulfide. What I want you to do is look at both 4 and 2 and what do both of these numbers go into, and you'd say, oh yeah, they both go into the number 4. So therefore, I need only 1 10 and I need 2 sulfurs, and that is the correct formula for stannic sulfide. This is not correct. Now, there is one step you can do to make this one correct, and if you know this, this is really important. When you write an ionic compound formula, it always has to be in the simplest whole number ratio, the empirical formula. Simplest ratio, called the empirical formula. Since both of these numbers can be divided by 2, if you divide both by 2, you come back to the correct answer, SN, S2. But I like this method better. You don't have to do an extra step there. It's what do both numbers go into. If you'll do it that way, you'll do much better. And again, there's a naming video. Watch it. Okay, so they're showing the crisscross method. I don't like it. What I'd rather you do is say, what do 3 and 2 both go into? It's 6. I need 2 3 positives and 3 2 negatives to make it neutral. So +6, -6 equals 0. Same thing here. What do 2 and 3 go into? 6. I need 3 calciums and 2 phosphates. Now the phosphate's a polyatomic ion. So if you got more than one polyatomic ion, you do have to use the parentheses here. You have to use the parentheses. If you have more than one polyatomic ion, put it in parentheses and put the number outside as a subscript. Now another thing, when you're working on these, if you're getting the wrong answers in Connect, watch the Connect orientation videos on how to use the chemistry palette. You have to know how to use this correctly in Connect in order to format your answers correctly. So orientation video posted at the top of your Connect assignments. Watch that multiple times to learn how to. And again, if you don't see this chemistry palette, it's because your pop-up blocker is turned on your browser. So make sure you run that troubleshooting and that you get all green checks to make sure that the chemistry palette will pop up. All right, so notice the name. You name the metal by its full name, aluminum. Change the nonmetal to an IDE ending. This is aluminum oxide. This metal is calcium, and then you have to memorize the name of this polyatomic ion called the phosphate ion, so this is calcium phosphate. Notice we don't say things like aluminum 3 or aluminum 2, oxygen 3. We don't say anything like that, or 3 calcium, calcium 3, phosphate 2. We don't do that because the charges determine what how many of each we're going to have present. So notice we don't have to say calcium 3, phosphate 2. It's already understood. I'm going to have 3 calciums for every 2 phosphates to have a neutral compound. All right, so this is the decision-making chart for ionic compounds. So the first thing you have to decide, are ions present? If ions are present, positive and negative ions, we're talking about ionic compounds. If the cation is a metal or a polyatomic ion, and the anion's monoatomic or polyatomic, so we got to sort through this, what this does. So if the cation only comes in one possible charge, like the alkali metals, the alkaline earths, or these transition metals, or aluminum, you name the metal first by its full name, and you change the nonmetal to an IDE ending. If the cation has more than one charge, like iron comes into 2 positive or iron comes into 3 positive, we call it polyvalent, then you have to determine which one you have. You do the metal, then you do the Roman numeral in parentheses, and then you change the non-metal to an IDE ending. And for a few of them, I want you to know the old system as well. Again, I have a naming video I will post that I want you to watch to get this down. It's that important. So, if you understand what we've done, you should be able to name all 3 of these compounds. So stop the video, see if you can name them. If you can't, then it's time to stop, read the book, watch the naming video, then come back to this lecture and go from there. But I will name these really quick, so stop the video. When you turn it back on, I'll give you the names. Okay, so the first one, the metal is out of group 2. Oxygen's out of group 16, so we just say magnesium oxide. That's the name of it. Magnesium, name the metal by its full name, change the nonmetal to an IDE ending, magnesium oxide. The next one is aluminum's 3 positive. OH is a polyatomic ion with a -1 charge called hydroxide. This is aluminum hydroxide. The last one is the tricky one. So the iron is 3 positive, and the sulfate is a polyatomic ion with a -2 charge. And both of these go into 6. That's why you have 2 irons here, and you have a total of 3 sulfates here. When we go to name it, though, it's not the number of iron, it is the charge on the iron. Not the number of iron, the charge on the iron that we use to name this compound. So in the stock system, this is called iron Roman numeral 3, and then that polyatomic ion is called sulfate. In the old system, the 3 positive iron ion is called ferric. So this is called ferric sulfate. Oops, excuse me. So the iron becomes ferric sulfate. So ferric sulfate. Okay. So the other thing you have to be able to do is, given the, so what we just saw was you were given the chemical formula, and you had to write the name. Now the other thing has to be able to be done, which is, given the name, write the chemical formula. So we look at this problem, and the first one is Mercury. I think I'll change colors here just to change it up. Mercury One Chloride. So this is one that I've asked you to memorize. So Mercury 1 is Hg 2 positive, and it's 2 mercuries bonded together. So it's a subscript of 2, and those 2 mercuries bonded together has a 2 positive charge, and that's what we see right here. And then chloride, you know, means Cl negative. What do both 2 positive and 1 go into? It's 2. So the correct chemical formula is Hg2Cl2. Now, this is a rare case where you do leave this as the double 2s here. That tells people that you are dealing with Mercury One Chloride. So the next one, I don't expect you to memorize chromate. There it is. But I do expect you to know that lead 2 is lead with a 2 positive charge. Both of these go in the number 2, and so the correct chemical formula would be PbCrO4. Notice we don't use parentheses around the chromate because you only have one of them. And then the last one, potassium, positive 1, it's out of group 1. Hydrogen phosphate. Well, phosphate is PO4 negative. If you add a hydrogen to it, it becomes HPO4 negative. So both of these 1 and 2 go into 2, so you need 2 potassiums for every 1 hydrogen phosphate. So you can see if you don't memorize your polyatomic ions, you're really going to be hurt. And again, watch the naming video that I've referenced many times. All right, Oxo Anions. This is where oxygen is the central atom. And then here's some examples. We've got chlorate, nitrate, sulfate. And I'm going to let you read this. You can click through this, but I do an extensive talk about this in my naming video. So I'm not going to go through this again. You can read this and then you can watch the naming video, and between the two, I think you'll be fine. But I've actually already done this. It's, you know, perchlorate, chlorate with the 3 here, chlorite with 2 oxygen, and hypochlorite. And like I said, my naming video does a good job with this, so I'm going to bypass this one for right now. Alright, so I do expect you to be able to name those after you watch the video. The first one would be perbromate. Second would be hydrogen carbonate. The last one would be sulfite. And we've talked about that. If it's sulfur with a 2 negative charge, that's sulfate. If it's sulfur with 3 oxygen and 2 negative charge, it's sulfite. When you knock an oxygen off, the ending goes from 8 to 8. All right, let's talk about hydrates and what they are. So when ionic compounds have water attached to them, that's what this dot represents. It represents that water is attached to the ionic compound, the salt. So it's not bonded in with the barium and chlorides or the barium ions and the chloride ions. It's attached to the barium chloride. So when water's attached to a salt, it's called a hydrate. And they have totally different chemical and physical properties. Here's an example of probably copper 2 sulfate. It's a nice, when it's copper 2 sulfate pentahydrate, it's a nice blue crystalline solid. When we take all the water out, it's a white powder. So when you take all the water out of a hydrate, it's called anhydrous. Anhydrous means without water. So you need to know that term. So this would be anhydrous copper 2 sulfate. Remember, copper is one of those polyvalent, comes in a positive 1, positive 2. So in the stock system, this is called copper 2 sulfate. This one over here is called copper 2 sulfate, but then there's 5 waters attached to it. So it's called copper 2 sulfate pentahydrate. Penta stands for 5. So we're going to use prefixes mono for 1, di for 2, tri for 3, and we're going to see these coming up in another one. Tetra for 4, penta for 5, hexa for 6, hepta for 7. And again, I have that in my naming video, so I'll stop there. But we're going to see it on another slide as well. So hydrates are ionic compounds, metal with nonmetals, ionic compounds that have waters attached to them. So if I put this copper 2 sulfate pentahydrate in an oven that's above the boiling point of water, the water will escape from this and become anhydrous. Okay, we're starting section 2.7, and in 2.7 we're changing gears here. Everything we've done up to this point has been ionic compounds, and with ionic compounds, what drives the naming as well as the writing the chemical formula is the charges on the ions. And so that's why it's so important that you memorize the charges of the ions and the polyatomic ions so that you can put them together to come up with the correct name. So again, for example, if you have let's try something different. Calcium let's try calcium nitrate. All right, so this is an ionic compound. So you have calcium and you have nitrate. And so you knowing that calcium is a metal in group 2, it forms a 2 positive ion. Because you've memorized that group 2 ions, group 2 metals form 2 positive ions. And then you've memorized that this is the nitrate ion, a polyatomic ion, and it has a -1 charge. And that both of these numbers go into 2. And so it's 1 calcium, and then it's going to require 2 nitrate ions for it to be electrically neutral. So that's what we've done up to section 2.7. Now we're going to start talking about nonmetals bonded to other nonmetals. There's not going to be charges, and so we have to have a different way of naming these compounds so that we can, by name, determine the chemical formula. This naming system for molecular formulas is easier than what we did for ionic. You don't have to memorize a bunch of charges or polyatomic ions. And what I find is students, once they learn how to name molecular formulas, they want to use that for ionic compounds, so don't make that mistake. Again, the naming video I'll post along with this lecture will delineate between ionic compounds and covalent compounds. All right, so let's look at molecular formulas. So molecular formulas, we're talking about a molecule. So what is a molecule? A molecule just means 2 or more atoms bonded together through a covalent bond. So we're not talking ionic now. We're talking about how do you bond 2 of the same atom together, like hydrogen. Well, hydrogen will bond with itself, and notice there's no positive or negative charges here. It's just the sharing of electrons between the 2 hydrogens. Or we know water, and we know that water is H2O, and the 2 hydrogens bond to an oxygen. Again, there's no electrical charges here. There's no positives or negatives, but there is a bond, a force that holds the hydrogen to the oxygen, and we call that a covalent bond. So when we're dealing with molecules, we are dealing with covalently bound compounds. Now let's describe some of these molecules. So the first one is diatomic. What does that mean? Well, that means 2, diatomic, 2 atoms bonded together. So this is an example of a diatomic molecule. Now, some elements on the periodic table naturally occur as diatomic. So I want you to memorize this. It sounds like a person's name, Han, Cliff, Burr. Cliff Burr. all of these elements on the periodic table naturally occur as diatomic substances, or diatomic molecules, if you want to say that. Again, remember what a substance is. It's either an element or a compound. In this case, these are all elements. It's not a compound because it's not two or more different atoms bonded together, or two or more different elements bonded together. It's two of the same element bonded together. All right, so we have then, once we have atoms bonded together, they're either homonuclear or heteronuclear. If they're homonuclear, it's two of the same atom bonded together. Again, hydrogen bonded to itself. Over here we have carbon. Actually, it's triple bonded to an oxygen. We'll learn that later. Carbon's black, oxygen is red. This is carbon monoxide, and it's heteronuclear. It's two different atoms bonded together. Once we get beyond two atoms bonded together, it's called polyatomic. So this is methane. This is a carbon in the middle attached to 4 white hydrogens. And so this is methane. It's a polyatomic molecule. Again, all of these substances covalently bonded, no charges, no positive or negative charges. All right, so then we have different kinds of formulas. You got to speak the language of a chemist. What are these different formulas? So a chemical formula just tells you what the composition is, like sodium chloride. That's a chemical formula. H2O, that's a chemical formula. It tells you what elements are present in the substance. A molecular formula shows you exactly how many atoms of each element are present. And so molecular formulas, we're talking about covalently bound compounds, and this is a molecular formula as well. H2O tells you that there's 2 hydrogens bonded to 1 oxygen. We could also have a sugar, C6H12O6. Tells us exactly how many carbons, how many hydrogens, and how many oxygens are in the substance sugar, each molecule of sugar. Then we have the word allotrope. I think it's weird that this one's actually on this slide because this is something a little different. This is an allotrope is where you have an element like carbon and it comes in different forms. So carbon comes in a graphite form and carbon comes in a diamond form. So allotropes are where you have an element and there are different arrangements of those atoms in that element, and it gives us totally different chemical and physical properties. Think about the graphite in your pencil versus a diamond ring. Another common example of an allotrope is oxygen. There's O2 that we breathe. It's a gas. And then there is O3, which is also a gas, and it's called ozone, but it's toxic compared to oxygen. So those are called allotropes, where you have just an element and the atoms within the element are rearranged to form different forms of the element, and we call those allotropes. All right, then there's structural formulas. Structural formulas shows not only the elements that are in the compound, but also the general arrangement of the molecules, or the general arrangement of the atoms within the molecule. So I wouldn't call this a structural formula. I don't know what the hydrogens are attached to. I mean, if I just looked at this and I didn't know anything about water, I may think it looks something like that. Now we're getting into a structural formula here. You see that the hydrogens are attached to the oxygen and not the hydrogens. We clean this up by actually using lines to represent the bonds between the hydrogen and oxygen instead of these dots. Here we have a ball and stick model. It even gives us more information. What we know about this model is, oh, water is not linear. It's actually a bent molecule. It's not linear. So this gives us even more information. And then finally, the last one here is called a space-filling model. It's structural. It shows, again, oxygen's in the middle. The hydrogens are attached to the oxygen, And it also gives us an idea of how much space each one of the atoms takes up. So you can tell by this the oxygen is larger than the hydrogens, and it makes up a majority of the volume of the molecule here. So structural formulas give us not only the elemental composition, but also an idea of what the three-dimensional or two-dimensional layout of the molecule is. So here we have a ball and stick model of ethanol, and it's a structural formula. It shows you that it's two carbons bonded together here. It shows you that there are three hydrogens attached to this carbon, and there are two hydrogens attached to this carbon, and then we have an oxygen here, and then we have our hydrogen here. And that's one of the things I want you to know, is that red represents oxygen, black represents carbon, and white represents hydrogen. It's important that you get the colors down because they give us a lot of information. So they ask you for the molecular formula. Well, the molecular formula at least tells us how many of each atom's present. There are a couple of ways to do this. You could just basically say it's 2 carbon, and then you could say, okay, it's 6 hydrogen, and it's an oxygen. And that would be fine. That would be the proper answer. And so that's fine. You could leave it that way. I almost automatically, when I write this, though, I write CH3, CH2, OH. Now, I agree that's more of a structural formula. It gives you an idea of how it's attached. So we'll go with this, but again, this also tells you how many of each element's present as well. It gives you a little bit more information. But for the bottom line, just to show you what elements are actually present in the compound, this is fine. Okay. All right, so we're going to name compounds, molecular compounds, covalently bound compounds, nonmetals with other nonmetals. So if we bond 2 elements together, just 2 different elements, they're called binary molecular compounds. So when we're naming a binary molecular compound, you will name the first nonmetal by its full name, and you will change the ending on the second nonmetal to an IDE ending. Again, that's so we don't confuse, in this case, chlorine to chloride. Those are 2 different things. Same thing here. Silicon is Si. Carbon is carbon as a bonded to silicon becomes IDE, so carbon becomes carbide. So we always change the second element to IDE to say, hey, we're not talking about an element, we're talking about a compound. So these are binary compounds. Now, once we get more than one atom or element bound with another element, we have to use prefixes. You have to memorize table 2.4. There's no getting around it. Now, most of these you already know. Mono, di, tri, tetra, pentagon, hex. You know, you've heard of maybe hexagon, like bees make their where they store their honeys in a hexagonal shape. Hepta may be new to you. Octa, you know from a stop sign. Nona means 9, and deca means 10, like a decathlon. So memorize these. There's no getting around this. We're going to use these from here on out. And just make you some flashcards with this. All right, so with nonmetal compounds, covalently bound compounds, molecules, molecular compounds, if you want to call them that, we have to tell the person how many of each element is present. Because if we don't, I don't know what the formula is. If you just say carbon and oxygen, or carbon oxide, I don't know what that really means. Is it carbon monoxide or carbon dioxide? So I can tell you mono is not used consistently, but we do use it for CO, carbon monoxide. So we state the first nonmetal by its full name, change the second nonmetal to an IDE ending, And for this one, we do use the word mono. And though mono ends in an O, we don't double up on the O's here. If the element begins with the vowel, we drop the vowel off of the prefix. All right. So for the second one, we have carbon dioxide, and so in this case, we do keep the I and the O since they're different. And again, this is saying 1 carbon and 2 oxygen, carbon dioxide. So that's how we can go from this chemical formula to this name. I mean, I did the opposite, from this name to that chemical formula. All right, sulfur dioxide, again, from this name, we could write this chemical formula. Or we can do this. We can look at this and go, that's sulfur and 3 oxygen, so I would call that sulfur trioxide. So you can see this naming is much easier. It's very straightforward. If you only have one of the first element, you just state the name of the element. Whatever number you have of the second element, you have to use a prefix for that. And let me just say again, mono is not used consistently. Like we just saw, let me back it up here. So if technically we were using mono correctly, let's back it up another one. This would be called hydrogen monochloride, and this would be called silicon monocarbide. So I can tell you that mono, about the only time we use mono is with carbon monoxide. Other than that, we generally don't see that. All right. Next one, nitrogen dioxide, easy. And then here we get a new one, a change up. We have 2 of the first element, so we have to use a prefix of di out in front here. So this is dinitrogen. Penta ends in an A, but the oxygen begins with the vowel, so we just say pentoxide, dinitrogen pentoxide. So this is how we use the Greek prefixes to make sure everyone knows what we're talking about and how many of each element are bonded together in the molecular compound. All right, so what I was just saying, if for ease of pronunciation, we usually eliminate the last letter of the prefix that ends in O or A when naming an oxide. That was. All right, so let's see if you can name these 2. If you can do this, you're in great shape. These are easy. If you can't name them, again, I've got a whole video on this. By the time you get through that video and do the homework, you'll be fine. All right, stop the video and write down the names of these 2 molecular compounds. All right, so the first thing you have to recognize when you look at these is that it's a nonmetal to nonmetal. It's a nonmetal to nonmetal. So we're dealing with molecular compounds, and we use a different naming system than ionic. So in molecular, we have to tell the person how many of each element is present since there's no charges. So the names are nitrogen trifluoride. Tri stands for 3. The prefix for 3, and here we have 2 nitrogen, so dinitrogen. Instead of pentaoxide, it's tetroxide because it's a 4 here. These are real easy. I don't generally see students missing those. The only thing I see is students trying to apply the molecular naming system to the ionic system, and that's where it fails. All right, then you have to do the opposite. Given the name, write the chemical formula. And this is what's going to happen. You're going to be taking lab, and you're going to be reading. It says, please get some sulfur tetrafluoride and combine it with hydrochloric acid. You don't have time to look up every one of these elemental symbols or molecular formulas because, you know, it would take forever, and you should be able to identify from your reading what the bottle looks like as far as what the label is on the bottle. So in this case, sulfur tetrafluoride, you go, okay, that's sulfur, that's fluorine, and there's 4 fluorines attached because it says tetra, so there's sulfur tetrafluoride. The next one is tetraphosphorus, so you have to recognize the elements. There's phosphorus is P. There's 4 of them because there's tetra. And then decasulfide says, okay, there's sulfur and that there are 10 sulfurs attached. And you know this is at the end because it has the IDE ending. You know the fluorine's at the end of the molecule because it has the IDE ending. So again, you have to be able to not only, given the chemical formula, write the name, but given the name, write the chemical formula, back and forth. Now, there are some compounds that they don't follow the molecular naming convention. And the reason why, they've been around much longer than this convention, and we already knew them by these names. So, like water, we don't call that dihydrogen oxide. That's the way we would actually name it if we were using the molecular naming system. We don't call ammonia nitrogen trihydride, although that would be the proper name using the molecular system. Hydrogen sulfide, we would normally say this is dihydrogen sulfide, but it's been around so long, this is what gives you the rotten egg smell around sewer plants, or a rotten egg actually. So we don't say dihydrogen sulfide, we just say hydrogen sulfide. Those are the 3 main ones I want you to know. I do want you to know this when it comes up later on. Phosphine is a poisonous gas. And if you don't know what phosphine is, you wouldn't know it's phosphorus trihydride. So make sure you know that one. It's nice if you know that one. I'm not as interested in it. This comes up quite a bit when we start talking about compounds with silicon. But I think these 2 I'm not as interested in at this point. I think you'll get more exposure to those names when you take organic chemistry. So these are common names. Common names, they don't follow the molecular compound naming system. All right, the acids, I'm going to skip over this. You can look up, I'll go through the slides and you can read them if you want to, but I have a video on acids naming and I will post that and you'll be able to watch that. So again, what is an acid? When it dissolves in water, it generates the hydrogen ion. That was the first definition of a Arrhenius acid. So it generates the hydrogen ion. It generally will it has a telltale sign of, it'll look like this. It'll be a non-metal compound. And then you'll see an AQ out here, which means aqueous, which means dissolved in water. This is called a binary acid because it's just 2 elements bonded together. And then we have oxyacids like sulfuric acid. So they're going to have hydrogens, and then they're going to have a polyatomic ion on the other side there. This is still a molecular compound, and it's called an oxyacid because there's oxygen in the compound. These have different naming systems, and that's what the video is about. So at the bottom of this slide, hydrogen chloride, when we bubble it through water, hydrogen chloride's a gas. This is a gas here, HCl gas, hydrogen chloride, non-metal, molecular compound. When we bubble it through water, we change that to an ic ending and we call it an acid. And once it becomes an acid, it's HCl aqueous, AQ. For aqueous, dissolved in water. So here are some common acids that we're going to run across. These are the binary compound names, the molecular compound names. Once we bubble these gases through water, they become dissolved in water, aqueous, and they become acids. And all these are binary except this one. And just again, it was thought that cyanide was one substance, but we know it's not. And so it's a holdover from an older time, and so we call it hydrocyanic acid, even though technically it's not a binary acid. Oops. All right, next slide. So this is what I'm talking about. the other type of acids are oxyacids, like nitric acid, nitrous acid, sulfuric acid, and we could do sulfurous acid. The thing about binary acids, they are directly related to the name of the polyatomic ions, all right? That's the most important part. They are directly related to the name of the polyatomic ion. So here's my mnemonic for this, and I talk about it in my video. I ate something icky. If the ion, the polyatomic ion, ends in 8, the acid ends in ic. So this is the chlorate ion, ClO3 negative. When we attach a hydrogen to it, it becomes chloric acid. Now this one, this is the chloride ion. Ide ions become OUS acids, and the mnemonic for this is I delight, and I'm going to spell delight incorrectly. I delight in something delicious. I delight in something delicious. That's the way, that's the mnemonic to help me know that any ion, polyatomic oxyion that ends in ite, the acid will end in OUS. So that's just something to remember to help you get those down. I'm not going to go through this. This part is in my video. Other than, I will say these are, when you have more than one hydrogen ion attached, it's called polyprotic. It means it has so if you look at the difference between HCl and H2SO4, this has twice as many hydrogen ions than hydrochloric acid. So if this is 1 molar, let's not talk about that. I was ready to say I was going to give you a concentration unit. We haven't talked about molar yet, but so what I want you to know is if I have the same amount of these two substances, this gives me twice as much hydrogen ion. Let's just do that. All right, so determine the formula of sulfurous acid. I delight in something delicious. So there's the OUS. There's the ion it comes from, the sulfide ion. It's a -2 charge. Therefore, I need 2 positive hydrogen ions to bond with that to make it neutral. There's the chemical formula for sulfurous acid. Okay, this next section, this is what we're going to talk about when I get back, but I'm going to go on and do the video for this so that you can look ahead, and so that maybe frees up some time when I come back to do any review you want to before the exam. So we want to talk about organic compounds. Now, there's not going to be a lot of organic in this class, but we might as well get started on it because some of them, like that ethanol, that's an organic compound. And we're going to see ethanol. Acetic acid is generally indicated as an organic compound. So let's name some of the basic organic compounds. So organic compounds contain carbon and hydrogen, and then with a combination of other elements like oxygen, nitrogen, sulfur, or the halogens. So if we call it a hydrocarbon, it only contains carbon and hydrogen, hydrocarbons. So when you think of hydrocarbons, you probably think of gasoline or fuels or things like that, fossil fuels. So coal, hydrocarbons, all right? And so hydrocarbons are in a group called alkanes. Those are the simplest hydrocarbons. Alkanes are single bonded carbons, like so, and then carbon wants to form 4 bonds. So every place where we see one of these lines coming off of a carbon, there's actually a hydrogen attached. So there's hydrogens at every one of these bonds coming off the carbons. Those types of compounds are called alkanes. So hydrocarbons that have carbon-carbon single bonds and hydrogens are called alkanes. And we need to be able to name some basic alkanes. They come up quite frequently. So you've heard of methane. A lot of these are going to be the gases we hear about, greenhouse gases and so forth. So methane is one carbon bonded to 4 hydrogen. Ethane represents 2 carbons with 6 hydrogen. Propane, which we use to propane gas grill, is actually 3 carbons. Here they are in black, and there's the arrangement of the oxygen. So this is a structural formula that you see under these. These are ball and stick models, and they're structural formulas. And then maybe you've heard of a butane lighter. It's 4 carbons. There they are. And if you get the hang of this, you find out that all alkanes follow this rule. They are CnH2n plus 2. So when you have 4 carbon, you put a 4 in here. 4 times 2 is 8. 8 plus 2 is 10. So we better have 10 oxygen here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's an important formula to know, CnH2n plus 2. All right, here's some more. Notice these are using those Greek prefixes: pentane, hexane, heptane, octane, nonane, and decane. Notice the carbons are not in a linear fashion. They're actually what we call tetrahedral. It's 4-sided. There's a side created here. There's a side created here. And well, we could, it's hard. Let me show it this way. Here's a carbon. You've got a hydrogen here. You've got a hydrogen coming up here. You've got one kind of coming out at you like this, and you got one going back through the board like that. And there's 4 sides to that. There's one side. Here's the second side. There's one in the back there, and there's one below. So it's 4-sided, tetrahedral. So know these alkanes. Know that alkanes are just carbon. They are a hydrocarbon that consists of only carbon and hydrogen. And they take on the formula CnH2n plus 2. And they're going to help you with learning the prefixes that we use to name molecular compounds. All right, so once we have that backbone of a hydrocarbon, if we replace one of the hydrogens and we put on a different group, so we knocked off a hydrogen here and we put an OH group on here. So before there was a hydrogen here, we've knocked that out, we put an OH group. That's called a functional group. And the functional groups is what gives a hydrocarbon or an organic compound its chemical and physical properties. So C2, and then we have H6, that's ethane. It's a gas. It burns, much like methane. But when we knock a hydrogen off and put an OH group on it, it now becomes an alcohol. We call this ethanol. This is a liquid at room temperature. It's no longer a gas. It's a liquid at room temperature. Yes, it burns. It doesn't burn like ethane does, but it does burn. So just changing one hydrogen for an oxygen and a hydrogen totally gives this different chemical and physical properties. So when we replace one of the hydrogens with another group, that's called a functional group, and that functional group gives these substances the properties that of that organic compound. So OH, called an alcohol. The functional group is the hydroxy group. An aldehyde, now this is where it gets tricky. It looks like it's just carbon, hydrogen, and oxygen, but what it is, it's carbon double bonded to an oxygen, and then a hydrogen here. So you've heard of formaldehyde. Formaldehyde has this functional group within the organic compound, and that's what makes it toxic. Carboxylic acids, functional group, like acetic acid, and so it's carbon, double bond to an oxygen, and then you have an OH group, kind of like an alcohol here. An amine looks like ammonia. Like if you took ammonia and you knocked the hydrogen off, so now you have a free bond here for it to bond onto an organic compound, that forms an amine. And you're going to hear about those in biology, peptides, and then we get into DNA with this as well. Proteins. All right, the next slide here is about when we write chemical formulas, especially ionic compounds, we always use the simplest whole number ratio. Remember we had an example where I said SN2F4, and this is an ionic compound. This is a metal with a non-metal, and the 10 is actually 4 positive, and the sulfur is 2 negative. And I said this is the incorrect formula for this compound because it's not in its simplest whole number ratio. We can divide both of these by 2 and we get SnF2. 10, 4, oops, I really flipped it. Yeah, well, yeah, let me erase this. Let's change this F here to an S. And let's erase that one too. Change that to an S. So this would be 10,4-sulfide. That would be the name of the compound. So ionic compounds are always written in their simplest whole number ratio, called the empirical formula. So those are easy ones. Everybody gets those correct, that ionic compounds always written in their empirical formula. But where it gets difficult is when we start writing the empirical formulas for organic or molecular compounds. So water is that's its molecular formula. Well, that's also its empirical formula. There's no change in that. There's no whole number you can divide through by here and get whole numbers of hydrogen, oxygen. Remember, you can't have a fractional number of atoms. You either have an atom or you don't have an atom, back from Dalton's law. So here's hydrogen peroxide. Well, both of these can be divided by 2. So this is the molecular formula. It tells you exactly how many hydrogen and oxygen are in the compound. The empirical formula gives us the ratio of hydrogen to oxygen. It is the simplest whole number ratio of one element to another in the compound. So this model looks like this, but the molecular model looks like this. And you're looking at this and going, why do I need to know this? Well, this is where it gets to be like sugars. We go back to the sugar, C6H12O6. That's the molecular formula. Tells you how many carbons, hydrogens, and oxygens are in the sugar. But if I want to do a classification of sugars, I'm not just talking about this sugar. I want lactose, maltose, so forth. The empirical formula for sugars is CH2O. They generally form the formula CN H2N plus 2, or H2N, yeah, just H2N, and then ON. So if you put a 6 in for the N, we get C6, 6 times 2 is 12, and then O, we have oxygen, we have 6, so C6H12O6. Or you could have a sugar C7H14O7. So the empirical formula, the advantage of it is it allows us to categorize very quickly a whole group of molecular compounds. So down here we have acetylene, that's its molecular formula. Here's benzene, but when we convert these to empirical formulas, they both are a single carbon to hydrogen bonded substance. So whatever the repeating pattern is, the simplest repeating pattern is what we see here with these compounds. So empirical formula, simplest whole number ratio formula. Ionic compounds are always written in their simplest whole number ratio, unless it's something like the mercury that we talked about, where it's Hg2Cl2 to indicate we're talking about Mercury One. Molecular compounds, generally we like the molecular formula best. We generally like this formula best because it tells us how many of each element's present. But sometimes we want to classify a group of compounds, and we will use the empirical formula to do that. All right, so if you understand what we've just talked about, I want you to write the empirical formulas of each of these molecular compounds. These are all covalent compounds. Write their empirical formula. All right, so let's stop the video, hit pause, and then come back and see if you got the right answer. All right, the first one can be divided by 6. The second one can be all divided by 5. And the last one, nothing can be divided by and still have whole numbers. I mean, if you divide by 2, you'd have half of an oxygen. So the correct empirical formulas are what you see. Divide the first one by 6. We get CH2O. So again, classification of a sugar. Adenine. Classification of it's related to an amine. And then the last one, that is its molecular formula and its empirical formula. Can't be simplified any further. All right, compounds in review. And again, if you've watched my naming video, you've watched a video on naming acids. This is a summary. This is the decision-making chart of how you name any compound that we come across in General College Chemistry 1 and 2. So that's what you're really doing here. This is the sorter. This is the decision-making chart of how you're going to name any substance we come across in General College Chemistry 1 and 2. So a compound, we know by definition from Chapter 1 that a compound is 2 or more different atoms bonded together in a fixed whole number ratio. If it's ionic, that means there are positive and negative charged atoms present. There's cations and there's anions. And so if it's ionic, we're going to have charges. If there's no charges, if it's 2 nonmetals bonded together, 2 nonmetals, then we're not going to have charges. So that's your first decision after you know it's a compound. Is it ionic or is it molecular? If it's ionic, you have to go through this sort in order to name the cation and the anion. And the big thing is, does the cation only come in one possible charge? That would be like the elements in groups 1, 2, and 3. Or is it polyvalent like the ones I've asked you to memorize? They're generally the transition metals. The transition metals tend to be polyvalent. So that's the hard part. If it's nonmetal, it's real easy. That's why everybody likes this side. All you do is you look at it, you look at the nonmetals, you name the first nonmetal by its full name, change the ending on the second one to IDE, and you use the Greek prefixes to tell the person how many of each element's present. So yes, this side is much easier. Don't apply this side to the ionic side though. That's where you get into trouble. So if you can do that, and I know it's a lot of work, but this is the hurdle, and you've got time to do it. Put your time in, get the naming down. Once you get it down, nobody can take that away from you. It's going to help you both in the class and the lab and your biology classes. And people are going to be struggling. You're going to know the name. You're going to know it and you'll be confident, and it's going to build confidence in you working in a chemistry lab, speaking the language of a chemist. All right, here's some more common names, and most of these I do want you to know. We can't get around this. This is limestone. This is what we mine in Lexington. We've got limestone mines here. Then we have sodium bicarbonate, which is baking soda. We have magnesium hydroxide, milk of magnesia, water, ammonia, carbon dioxide, or dry ice if it's a solid. Sodium chloride, nitrous oxide, also called laughing gas. Instead of, we would normally call that dinitrogen monoxide. You never hear it called that. It's generally nitrous oxide. And then the last one, it's a hydrate. Instead of saying magnesium sulfate heptahydrate, which I do want you to know this name. That's a fair game question. But its common name is Epsom salt. All right. So that concludes the naming. And it is a lot, but it's not mathematical. So those of you that struggle with the math, this should be kind of balancing the math that we had in Chapter 1. So we'll stop here, and that covers all of Chapter 2. You now have the lectures recorded for Chapter 1 and 2, and that's what's going to be on the first test coming up. Thank you.